Good evening. Is it working? Okay. Welcome to the first Astronomy on Tap of 2017. My name is Charlotte, and this is Yair.
Hello.
And we're your hosts for tonight.
So thank you all for coming, despite the water falling from the sky, which we heard is a big scare in Santa Barbara. So thank you for braving that and coming out tonight. We have a great plan tonight. Here's what's going to happen. So we'll have our first speaker, Mike, tell you about cosmic fog. And if you have questions for Mike, you can text them to this phone number, which is 805-55-AOTSB. And yeah, so even though this is an unforgettable phone number, apparently people still forget it. So we're going to put the sign up here so that you have it. So during the talk, you can text your questions, and also during the break. And when we come back from break, we will answer questions that you sent. And then we'll do astronomy in the news. We'll take another break, and then we'll have our second presentation by Greg. You will send questions to Greg during his talk and while we tell you about the next events, and then we'll answer them right after. And at the very end, if you should each have a raffle ticket, and we'll raffle our now famous across the universe Astronomy on Tap beer glasses. Yep. So, okay, that's a plan. Now, we also have our last batch of posters and postcards to give away today. So if you ask a question and we choose it on stage, you can go to the back, to our friend Griffin in the back, and he'll give you, let you choose a poster. If you're a student, any kind of student, you can get a poster. If you're not a student, you can get a postcard. If you're not a student and you want a poster or you didn't ask a question, just hang out till the end and we'll give out whatever we have left at the end. So, yeah, if you're a student and we choose your question poster, anyone else we choose your question postcard, and anything we have left at the end, you're welcome to, regardless. Okay, I think we're ready to start.
Okay, so our first speaker tonight is Mike McCourt, who is a postdoctoral scholar at UCSB. And in addition, he's going to be telling us about clouds around galaxies and galaxies like our own. And in addition to being a very smart astrophysicist, we asked Mike to tell us about a few of his hobbies. If you come to Astronomy on Tap regularly, we like to show you that astronomers do more than just sit at their computers and write code or go to telescopes. So Mike told us that he spends a lot of time hiking when he's not doing astronomy, and he's been to some pretty cool places, including Tanzania and places in Africa. But the thing that we thought was really awesome, which not often astronomers, you would think that a lot of scientists have a creative side, but it turns out quite a few of them do. And Mike actually spends a lot of time building furniture. So this is a table that he built, and he told us that he's built more than half of the furniture in his apartment. And he may be taking commissions, so if anyone's looking for some furniture, maybe you should give Mike a call. And in addition to furniture, he's done some other types of carving, which are very impressive, including this pumpkin. So if you're also looking for good pumpkin carving, maybe Mike's the person to call. But tonight, he's not going to be telling us about pumpkin carving or woodwork. He's going to be telling us about clouds around galaxies. So, you ready? So yeah, if you please welcome Mike McCourt.
Awesome. Thank you for that. So I'm going to be talking today about actually a new result that's come out of UCSB. You will actually hear about this before most astronomers do. Oh, sorry. You will hear about this before most astronomers do, so I hope you're paying attention. But the big picture here is galaxy formation, and I figured I'd start with a little tour of some of the nearby galaxies. And so this is a simulation of the Santa Barbara sky in winter. And it's actually meant to be an accurate simulation. The only cheat I've done is I've sped up time. And so as we wait in just a second, we'll see the sunset, and we'll see the moon come up and the stars come out. These are the stars as you'd see them here if you went outside, if it weren't raining. And so you can see as time goes on, everything's revolving around the North Star. You see Cassiopeia in the upper left, and the Big Dipper is rising now. They point towards the North Star, and you can use them to find your way if you're lost on Earth. But since I'm an astronomer, I'm not worried about Earth right now. I'm going to take that away, along with the atmosphere, and we'll focus on the stars. And I'll put up the constellations as a little bit of a map to the stars. And when we zoom in towards the Andromeda constellation, hopefully it shows up. As we zoom in, you'll see there's something here that doesn't look like a star. It looks bigger than a star. And in fact, it's a lot bigger than a star. This is made up of a few 100 billion stars. And it's a few 100,000 light years across. And it's so far away that we're seeing this as it was 2 million years in the past. So this is a galaxy. We live in something like this, and this is our nearest neighbor. And as we zoom in a little bit further on this galaxy, we can see it has a companion. This is another galaxy. It's much, much smaller than the first one. This, instead of a few 100 billion stars, this has only about 3 billion. Even though it's a wimpy little thing, the few stars that it does have, they're packed into such a tiny little volume that if you lived in this galaxy, there'd be so many stars in the night sky that it would be as bright as our daylight. It would never get dark in that galaxy, and there probably wouldn't be astronomers. So those are our two nearest neighbors, and you can see how different in size and shape they are. That gives a sense of the diversity of what's out there. And we'll just zoom around for a little bit and take a look at some other neighboring galaxies. It's a beautiful image by the Hubble telescope. Zoom out, and then zoom in again to get a sense of the sizes of these things and the distances between them. Galaxies are mostly disk-shaped, and this is one that we happen to see nearly edge-on, so it looks like a matchstick. Unfortunately, there's a star right in front of it. Then we zoom out and zoom in again to a different part of the sky. This is another disk galaxy. We're seeing it nearly edge-on, but it's tipped just enough that we can see the shape of it. And so if you think like a CD or a DVD, that gives about the right perspective for these. This is actually two galaxies in the process of merging, which is an astronomer's polite way of saying they're crashing into one another. And another beautiful picture by the Hubble telescope. This is probably something similar to the one we live in. And this galaxy has a companion, a really funny looking thing. So I'll come back to this galaxy towards the end of my talk. For now, I'm just kind of giving you a sense of what's out there. And then most of the galaxies I've shown you are pretty isolated. They're huge structures, but the distances between them are much, much bigger. In a few cases, that's not always true. There are places that are sort of like galaxy parties, or maybe more like galaxy cities. There are areas of the sky that are just way overpopulated with them. So this is an example. And then I'll just show one more galaxy in a totally different part of the sky. And this is a funny looking one, but it happens to be one of my favorites because I've written a few papers about it. This is a very massive galaxy. It's at least a few hundred times as big as the one we live in. So that's just a sample of some of the nearby galaxies, ones that I find interesting. But the reason I care so much about galaxies is that we live in one. And so understanding how galaxies form and where they come from, that really plays a fundamental role in our history of the universe and how we came to be. And we know that we live in a galaxy because we can actually see it. If you're lucky enough and you've been in a place where the night sky is dark, far away from a city, you can see a band of light that stretches across the sky. We call that the Milky Way. And when you see that, what you're actually looking at, you're looking through the disk of our galaxy. There's an excess of starlight in that direction. So we know that we live in a galaxy because we can see it. Unfortunately, I can't show you a picture of our galaxy like I did with the others because we're inside it. There's no way to get outside to take a photograph. But that doesn't mean that we're totally in the dark. with a lot of hard work and some careful inferences, astronomers do have a pretty good model for what our home galaxy looks like. And so this is our best guess. It's not so different from some of the galaxies I showed you. And I hope you can see it, but this red circle here shows where we are. We're not exactly in the center. We're not exactly in the outskirts. We're sort of comfortably in the middle of nowhere. And the size of that circle actually shows all of the stars that you can see in the night sky. So we can see stars from pretty far, out to about 1,000 light years. But the galaxy we live in is at least 100 times bigger than that. It's 100,000 light years across. So this is a huge structure. It's hard to convey, actually, how big it is. And I'm not even going to try, because this is just the tip of the iceberg. It turns out that galaxies form inside much larger structures that we call halos. And the halo is at least 10 times as big and 10 times as massive as the galaxy. And if you study the way that galaxies form, it turns out the halo forms first. Some region of the universe collapses and makes the halo. This halo is literally made out of the universe, which I find amazing. And then this galaxy, the swirly disk of stars, is a secondary structure that forms in the center of that halo. And so if you want to understand how galaxies form and where they come from, you first have to really study how the halo forms. And that's really what I'm talking about tonight. So I colored the halo as kind of a fuzzy pink blob, and you'll see why in a second. And the word halo kind of makes it sound like I'm making this up. But I want to emphasize that these are real. Charlotte's going to talk a little bit later about some measurements that we use to probe halos. I'm going to show a more direct one, which is that occasionally we can actually see the halo. So this is an X-ray image of a nearby galaxy. It happens to be a very massive one. Some people call this the Skull Galaxy. And if you can't see why, I'll take a little liberty of Photoshop and fill in the details for you. But what you're seeing here is that halo. The galaxy itself doesn't shine in X-ray, but it would be about the size of this white spot kind of in the center of the image. And what you're seeing here is hot gas that's filling the halo. And we know the gas has to be hot, essentially because of gravity. Gravity is what formed this object in the first place. It's what caused a region of the universe to collapse, forming this halo. And gravity's always there. It always wants to pull everything in towards the center. And so if we see gas in the outer part of this halo, in spite of gravity, it's there because something's holding it up. And if you're gas, the only force that's available, the only force you have is pressure. Pressure requires the gas to be hot. And so if I balance the gravitational force with the pressure force, I can solve for the temperature of this gas. And it turns out it's about 100 million degrees. It's blisteringly hot. This is so hot that no atoms exist. It's so hot that this shines in X-ray light. And so that's why we can take an X-ray telescope like NASA has, point it at this galaxy and take an image of its halo. This is amazing, and it works really, really well. We can understand why the gas is here. We can understand why it shines in X-rays. We can understand its temperature and almost everything about it. The problem is that this is for a very massive galaxy. If we want to study a galaxy like the one we live in, it's smaller than this. It has less gravity, and so the pressure of the gas is a little lower, and it's not as hot. So whereas this is 100 million degrees, the gas in our galaxy is only about 2 million degrees. That's still pretty hot, but it's not hot enough to shine in X-rays like this. And so we can't take images of galaxies like the one we live in this way. But nonetheless, this is so basic and so simple, and it works so well, that until recently, I would have confidently said that our galaxy has to have gas like this. It has to be just like this, even if we can't see it. Unfortunately for me, some clever people in the last couple of years have figured out how to actually study and image the gas in the outer parts of galaxies like ours. They find something like this. That doesn't look so bad. It still looks kind of like a halo. But the problem is that this gas is only about 10,000 degrees. That sounds hot, and it is hot, but that's absolutely frigid compared to the 1,000,000-degree gas I was expecting. And remember, I got 1,000,000 degrees by balancing gravity with pressure. If that gas cools from 1,000,000 degrees to 10,000, it's lost 99% of its pressure. It has no way to hold itself up against gravity, and it has no business being out here. And yet this is what we see. It's completely unexpected. It's as though we'd walked into a lava field and found icebergs. Right? The lava is still probably there. It just happens to have icebergs floating in it. They're not melting, and we don't know why. And it's even weirder than this. And I think the real problem's a little bit subtle, but it comes down to the fact that when gas cools, it contracts. And so if I take this ball of million-degree gas that I expect, and I measure how big it is, and if I allow it to cool down to 10,000 degrees, when it cools, it's going to get smaller. This is what gases do when they cool. And it's cooled by so much, it's going to get smaller by a factor of 100. There's simply no way for it to take up that entire halo that it started out filling. And yet, when we look at it, this is what we see. So, we don't expect cold gas to be there. We don't think it can hold itself up against gravity. But even if we punt on all of the science questions why the cold gas is there, there's a geometric problem here that really doesn't make sense. In a telescope image like this one, we can measure how much cold gas there is. We can even measure how big it is. And then we can compare that to the volume of the region we find it in, and they don't add up. They miss by a factor of 10,000 or more. So there's a geometric issue that's very, very difficult to understand here. And so when we look in the outer parts of galaxies, we have real problems. We can understand from basic science principles that the gas out there has to be hot. Instead, we find cold gas. We don't know why it's there. We don't know how the cold gas can hold itself up against gravity. And then we have this geometric issue, that there's not enough material to fill the region of space that we see it filling. These sound like major problems. And it really starts to sound like we can't understand what's going on in the outer parts of galaxies. I'm going to try to argue that there's actually a very simple solution. One process will explain all three of these. And I'll explain it by making a terrestrial analogy, something that's actually kind of appropriate for today. So I'm what astronomers call a theorist, which basically means that people think I'm clumsy. And they don't trust me with fancy equipment or telescopes or anything that can break. So I get to use pens and paper and chalk, and I use a computer, but I don't actually get to go to it. I have to log into it remotely. But since I'm holding the microphone, I get to imagine whatever I want. And I could imagine that for one night at least, I get to be a real astronomer, and I get to go use a telescope. And I could come back and say that I've made the most amazing discovery. I didn't do any astronomy, but I did something that'll revolutionize meteorology, because I discovered that our atmosphere is full of liquid water. And I could say that I checked, and it's actually liquid water. It's 1,000 times as dense as air, somehow floating. I could confirm that it's everywhere. Everywhere I point my telescope, in every pixel of every image I take, I find water. And if I do a little math and calculate how much water there is, there's a meter's worth of water in the atmosphere. And so I might conclude that our atmosphere has a layer of these meter-sized balls of water that are packed in shoulder to shoulder, blocking out the sky. Each of them weighs as much as a truck. That would sound absolutely crazy. It would be crazy. This is like the situation we have in the outer parts of galaxies. But of course, if I did this on Earth, you would slap me. You would tell me that this is why I don't get to use telescopes, because I wasted an entire night of telescope time looking at a cloud. And we know that a cloud solves all of these problems, right? You normally don't expect there to be water in the atmosphere, but a cloud doesn't surprise us. If I have a ball of water, it would immediately fall to the ground. But if I divide that into little droplets and turn it into a cloud, we know that clouds float just fine in the air. And similarly, with this geometric problem, the total amount of water in a cloud is really pretty modest. It would barely fill a small room. And yet if I take that water, divide it into little chunks, and turn it into a cloud or a fog, you can cover a whole city with it. These are the exact same problems that we have in the outer parts of galaxies. And so when you see something creepy like this, when you see a telescope observation that you can't explain, really you should think that you're seeing a cloud. And in astronomy, there's no up or down, so I'm free to rotate things however I like. And another little secret in astronomy is that the colors in most of our images are made up. So I'm also free to recolor things however I like. And if I do a fair comparison, I think this looks pretty good. You'd be hard-pressed to know which one is which. So, this is the new discovery. Galaxies are foggy. This is not something that anybody expected, but they're filled with cold gas, where we didn't expect it, sort of like our atmosphere is filled with liquid water. And that cold gas, like a fog, it comes in the form of little tiny chunks that are scattered about throughout space. So that's kind of the first half of this research. The second half is understanding why galaxies should be foggy. And so we're studying this at UCSB using supercomputer simulations of gas. This is a simulation of gas, of cold gas, which is shown in white, as it would look if it moved through a galaxy halo. And if I zoom in and zoom in again, you can see that the gas is breaking up into little tiny chunks. They're spreading out throughout space. This is making something like a fog, which is exactly what we want in order to understand the outer parts of galaxies. Just another simulation showing the same thing. And this process is so fast and so violent that we're actually calling it shattering. That about captures the sense of what happens if you put gas in a galaxy. It just explodes into little chunks, and it wants to be something that's fog-like. Just something I want to show because it's cute. This is a photograph of actual fog. These are water droplets in air. And if I suggestively slide in my simulation results, they look pretty similar. And it's kind of a coincidence, but there's something called the filling factor. It's the ratio of the size of droplets to the distance between them. And it turns out that's pretty similar in galaxies to fog. And so when I say that galaxies are foggy, that analogy works pretty well, even quantitatively. So that's the paper that we submitted. It's a brand new result, and as I said, you've heard this before most astronomers have. One of the things that's really gratifying about this is that I'm just talking about fluid dynamics and physics here. I haven't said anything that's explicitly tied to the outer parts of galaxies, even though that's what I wanted to explain. And so I'm free to apply this wherever I want. And that's exactly what I'm doing. So I'll describe one new thing just because I happen to be excited about it. It's something called a galaxy wind. And you can think of galaxies as little factories that turn gas into stars. It probably doesn't sound like it, but you can get pretty far with that. And it turns out that they're very inefficient factories. Most of the gas doesn't turn into stars. It gets wasted, and it gets blown out of galaxies in something we call a wind. And that's what's going on here. The blue is the disk of stars in the galaxy, and then the red cones coming out of it, or you can think of them almost like exhaust. This is wasted gas that's being blown out of the galaxy. We have the same problems here that we have in the outer parts of galaxies. You can show pretty easily that the gas has to be hot, but they find cold gas. There's not enough of it to fill the volume that it's seen, so it's probably foggy. But there's another problem here, which is kind of interesting. The cold gas is moving really fast out of the galaxy, and we don't know how to make cold gas move fast. If you take a piece of gas in astronomy and you want to make it move, we don't have paddles, we don't have fans, anything like that. The only way you can make something move is to blow on it. And if you blow on a piece of gas, you can't get it to move. All you do is you destroy it. And so this is a supercomputer simulation that we've run showing that. I take a ball of gas and I blow on it. I don't actually get the dense red gas to go anywhere. All I do is I rip it apart. That was an expensive simulation, and I probably didn't need to do it because on YouTube, somebody's done the experiment for me. So this is a man trying to hit a water balloon with a baseball bat. And you can see the exact same thing happens. He doesn't actually get the water to move. In fact, the water is still moving backwards, right? All he's done by hitting it is rip it apart into little pieces. And so this is the same problem that we have in understanding galaxy winds. And it's a big problem. A lot of people are working on this, and we're trying to find ways to keep the gas from shredding apart, to hold it together for long enough in order to push it and make it move out of the galaxy. But after thinking about it more, I think this isn't the problem. I think this is the solution. If we allow the gas to break apart into little chunks, if we let that keep happening, we'll eventually end up with something like a fog. And the fog has no problem, if you blow on it, moving it with a wind. So I just wanted to say that 2 students now are really pushing this work forward. They're unfortunately too young to be here. They didn't clear the 21 and up threshold. They're old enough to do this research, but not enough to hear about it. But they're running new supercomputer simulations. They're really studying this fragmentation process and making a mathematical theory for how it works. And so we're in good hands. So just a quick summary. I talked a little bit about galaxies. I showed the variety of galaxies and that they live in much larger structures called halos. Halos have this mysterious name, partly because they've been invisible until recently. And the new data coming out, it's really weird. I tried to argue that it's not actually that weird, but that it's just foggy. You can interpret the data that way. And then I showed that there's a physical process that makes fog in galaxies. If I try to put cold gas in a galaxy halo, it explodes into little fragments, making a fog. That's exactly what we want to see. I tried to argue that the shattering and this fog, they solve all of our problems. It's been fun to work on. And then I just wanted to mention that pretty much everything I've talked about today has come out of UCSB in the last couple of years. The observations, the mathematical theory, the supercomputer simulations. And so, yeah, it's been a fun place to work on for the last couple of years. So, thank you.
Thank you very much, Mike. Okay, so if you have questions for Mike, we're going to do questions after a 5-minute break. So you can text your questions to this number, and it will also be on here as well. So yeah, text to the number that I don't actually remember. Sorry. And we forgot to say at the beginning, but anyone you see wearing, where is mine? A flashing star is a professional astronomer or someone who works at LCO. So if you have any questions about anything else to do with astronomy, please come and talk to us during the break or whenever. So yeah, 5-minute break.
We got like 50 questions or so, we're not going to have time to go over all of them. I apologize in advance. We got some really good questions. I'm just going to pick a few. So I apologize if we don't choose your question, and want to remind you that after the event, we'll be hanging around for a while, so you can ask Mike or other star-pin wearing astronomers any questions that were not answered, so feel free to stick around at the end. And so for now, I'll have to just pick a few. We're going to start with a quick and easy one. Someone asked how you made the graphics in the presentation. I'm assuming the simulation at the beginning of the night sky. Want to mention what that's called?
Oh.
Yeah, how was that simulation of the night sky made in the first slide?
Yeah, it's a wonderful free program called Stellarium. It's like a night sky simulator, and it's free. Anybody can download it. You can get the source code and change it however you want. It's a very fun thing to play with, and it's a nice thing that those people did.
Okay, so now a really good question that a lot of people had was, you say it's so hot that atoms don't exist. So what is the gas made of at those temperatures?
Oh, right, so an atom is made of a nucleus that's made of protons and neutrons. And then there's a cloud of electrons that surround that. And the electrons are really kind of what determine the properties of atoms. They determine the chemical reactions that they make, and largely how they interact with light and how they, all of the senses we have, color, taste, feel. So when gas gets really hot, you rip the electrons off of the atoms, and you just have charged particles flying around. There's no chemistry, it's different from the type of stuff we're used to dealing with. It also makes the gas electrically conductive, which means that things like magnetic fields matter. It behaves almost like a metal in that sense, but it's a gas. This is one of the things we have to deal with in astronomy, but it's very different from what we're used to on Earth. So it's kind of like a gas, just with very different properties.
Okay, so it's not water like clouds on Earth. That was just to reiterate an analogy of what the gas behaves like, but it's actually atoms or nuclei and electrons just zooming around.
Zipping around, yep.
And so the other question was, if it's not atoms and it's just this gas zooming around, what's heating it? What's making it so hot?
Oh, good. So I avoided that question. I said that in order to be there in spite of gravity, it has to be hot. That doesn't say what it is that made it hot. And that answer is actually gravity. So as this galaxy is forming, gas falls in towards it. And as it falls in, gravity is accelerating, and it's going faster and faster and faster and faster. And then eventually it hits the edge of the galaxy and it stops. And when that happens, the kinetic energy that it has from moving, all of that energy associated with motion, the gas smacks into the edge and stops, and that goes straight into heat. And so the gas heats up almost instantly when it hits the edge of the galaxy. And then it's so hot that it stays that way for a long, long time.
Okay, so related to that process, there was a question of how long does it take a halo in a galaxy to form?
Roughly a large fraction of the age of the universe. It's a, it's a process that happens as the universe expands. So the universe expands from the Big Bang, and when it started out, it had little fluctuations in it that were basically sound waves bouncing around in the early universe. And parts of that expand less fast. And so as the universe grows out of the Big Bang, these fluctuations amplify. And some of them get big enough that gravity becomes so strong it actually pulls them in. They stop expanding and they collapse. That's how you get halos. But it's a long process.
So someone asked about the density of this gas, right? Again, we're used to thinking of gas like air or in clouds as water droplets. How does the density of this gas compare to that?
That's a great question. So even in that Skull galaxy, where the gas is 100 million degrees, you would still freeze to death if you were in it. The density of the gas is so low. I only know it in astronomer units, but 10 to the minus 4 particles per cubic centimeter. It's fantastically empty. It's much, much, much more empty than the best vacuums on Earth. So yeah, the gas is hot in the sense that particles are zipping around. But if you were in it, it's so empty that there's so few particles hitting you, it wouldn't keep you warm. You would still freeze to death.
So someone had asked about that Stellarium simulation, which he says just a free program anyone can download and use. There was another question about the simulation that you did on the supercomputers. So someone's asking what program is that and how many CPU hours did that take?
So these were pretty expensive. They were a few 100,000 CPU hours, which is the way that we describe how supercomputer simulations run. So if I ran it on one computer, it would take a few 100,000 hours, which is 10 years, if I did that right. But we don't run it on one computer. We run it on a supercomputer that has lots and lots of processors. We divide the problem up and run them together so that I can actually get results in a couple days. So we have software in the astronomy community that we've written to solve these equations. We use them a lot. I'm not sure that they're that interesting to non-astronomers. But they solve our equations. We run them on supercomputers, and then I make pictures like this.
Okay, yeah, just to say that this is not like software you just download and run. What a professional astronomer like Mike does is write some of this software, right? And you have to know how to run it. It's not just to click a button. It's much more complicated than that. So Stellarium you can download and use for free. This software, you need a few years of academic education probably to run. Okay, so I think that's all the questions we have time for now. So let's thank Mike again. And it is now time for Astronomy in the News. Okay, so I think Charlotte's going to get us started here.
Okay, so how many of you, or any of you here on the very first Astronomy on Tap? Okay, it's so bright I can't even see. I saw like one hand there. So at the very first Astronomy on Tap, we actually talked about a fight between astronomers over this very mysterious thing called a fast radio burst. And a fast radio burst is a very energetic, very brief burst of radio waves that were first discovered in 2007. And they're completely mysterious. They happen randomly around the sky. We didn't really know where they came from or what causes them. And the fight that we described last year was one group of astronomers basically said they discovered where one of these had come from, and another group said, no, you're wrong. But earlier this year, in January, beginning of this year, one group has claimed that actually they really have discovered where a fast radio burst came from. So these are notoriously hard to pinpoint because they just happen so randomly. I really only discover them by chance. And most of them are discovered by a really large radio telescope in Puerto Rico called Arecibo. And Arecibo is really big, so it can look at lots of the sky, but it's got a really poor resolution, so that it basically means everything's really, really pixelated. So it's really hard to tell exactly where in the sky the light is coming from. So what I'm showing you on the right-hand side, you see this square, and inside it there are two circles, two white circles. So those circles were the regions that this particular fast radio burst, that we knew that it was coming from with the observations from this telescope in Puerto Rico. So it's a pretty big area of the sky. So it was from somewhere over there, but we're not really sure where. But this fast radio burst was pretty special because it seemed to be repeating. It happened at least 10 times that were measured. So some astronomers thought, okay, so we think we know sort of where it is, and it's probably repeating, so we'll go look at it again. And they looked at it again, and with this array of telescopes, which is called the Very Large Array, so you know astronomers are very good at thinking of original names for their telescopes. This is in New Mexico. And they basically just hoped that it would go off again. So it's quite expensive, when you want to use a telescope, you're competing with lots of other people. So they really just had to hope that it would go off again. And luckily for them, it did. It went off actually 9 more times. And using their data, they were able to pinpoint exactly where it came from in the sky. So if you see these two circles, so that was where they knew it was coming from before, they actually pinpointed it to that tiny little white square that's in between those two circles. So that was what they were able to do with the VLA, with the Very Large Array. So then they went and looked at that area of the sky, and they realized that that was pointing at a very, very tiny galaxy that's actually very, very far away from Earth. It's about 2 billion light years away. And that galaxy also seemed to have a supermassive black hole in it, which is kind of weird because only really big galaxies are expected to have big, supermassive black holes. So it's kind of weird. But this is where this fast radio burst is coming from. So I don't know what does that really tell us? So now we've actually pinpointed it. It does tell us a few things. So up until this discovery, we really had no idea where they were coming from, and there are probably more theories about what they are than actual measurements of fast radio bursts. There's only been 18 measured. But this tells us a few things. So some of these theories about what they could be said that the fast radio burst could be coming from inside our own galaxy. So this definitely rules that out. This is definitely coming from another galaxy. And because this one is repeating, we also know that it can't be an explosion that's happening that's causing the fast radio burst. If there was an explosion, then the thing that caused the explosion would probably disappear. So this has to be something that still survives to re-emit again. So the authors think that this study think that maybe it's a supernova remnant being sort of energized by a rapidly rotating neutron star, which is also known as a magnetar. So something pretty mysterious sounding still. But there's a lot of mysteries out there in the universe, and we're getting a little bit closer to understanding what these things are.
Aliens, right? It's obviously aliens.
It's not aliens here.
Okay. Okay. So this is really exciting because we have a ton of these fast radio bursts. We only discovered 18, but they're so short that the fact that we even saw 18 means they have to be super common. So the universe is just filled with these radio pulses that we have no idea what they are, but at least now we know where one of them is coming from. Okay, so while we're in the business of revisiting old news stories and seeing what happened to that, a year ago there was a story of brightest supernova ever measured, and supernova is an explosion of a star, and so these things are pretty bright. They shine like 100 billion times more than the sun, but some of them are still brighter than others, and a year ago astronomers thought we found the brightest one, and this is a problem because it started reaching the limit of how much energy we think an exploding star can actually produce. It was a bit too bright, and so this was really interesting. But, you know, a few of us were skeptical about this for several reasons. First of all, yeah, this problem that you probably can't make, it's not clear if you can make that much energy from an exploding star. This explosion did happen in a massive galaxy, so not the little tiny ones where we see this fast radio burst come from. And it happened in the center of this very massive galaxy, where, as Charlotte said, that is where we do expect supermassive black holes to reside. So a couple weeks ago, we had a paper published in Nature Astronomy a couple of weeks ago involving our observatory here in Santa Barbara that basically says, no, this was not a supernova at all. This was something else. This was another very gruesome way for a star to die. It was a star being torn apart by the supermassive black hole in the center of the galaxy. And so if you were here on our April Astronomy on Tap, you heard a lot about that. And the star getting torn apart by a black hole is something that's very rare but can happen, and that can produce more energy and explain some of the other properties of this star. Now, it's one thing is important when you see images like this is not at all what we see. This is actually not even real. It's just some graphic that someone did for the press release. You know, this might be what it looks like. We can go a step a little bit closer and show you a computer simulation of what it looks like. So the black hole would be in the center. You can't see it. And this stuff is the star. This is a star that got too close to a black hole. It doesn't look like a star anymore. This is what happens to it. So it starts orbiting the black hole, and it starts colliding with itself. And all of these collisions produce energy. And that's what we think was actually observed for that event, is these collisions. And then it starts funneling onto the black hole. And that makes a second flare, which we actually saw later. And so that seems to fit what's going on here. So, you know, we're saying this was not a supernova. This was a star being torn apart by a supermassive black hole. There is one little problem with our theory, which is the supermassive black hole in that galaxy is supposed to be so supermassive that it wouldn't do this. It would swallow the star whole and we wouldn't see anything. Unless it's spinning, and we think black holes spin. And so if we're right, this is going to be the first ever measurement of the spin of a supermassive black hole thanks to a star that destroyed it in a distant galaxy. So yeah, that was our conclusion. But really the thing is we'll have to just wait to find more of these and see if they can all be explained by this idea or not. Okay, so our next story, you know, a lot of celebrities died in 2016, but there's one you might not have heard of, and we want to talk about her today.
Okay, so this is Vera Rubin, who was a giant in the astronomy world. She was an astronomer who spent most of her career working at the Carnegie Institute, which is in Washington, D.C. And she's really known for her work that basically showed that more than 80% of all of the matter in the universe is invisible. So this is dark matter. And she did this by studying the way that galaxies move and how gas and stars rotate around galaxies. And to understand why you would start by, why would you want to do that, you can think about the solar system. So this really goes all the way back to the 1700s when Johannes Kepler made very precise measurements of the planets' orbits in the solar system. So you can just about see this, but so this is a sort of simulation of the solar system with the sun in the center and the planets moving around the outside. And what Kepler realized was that the further away a planet was from the sun, the more slowly it rotated around the sun. So if you were to look at a graph of the rotation speed of a planet versus its distance from the sun, the closer in planets like Mercury and Venus go really fast, And the more distant planets, like Uranus and Neptune, are much, much slower. So you can sort of see this was how the solar system is working. And a few decades later, Newton worked out that this was all to do with gravity, that the sun's gravitational effects were causing the planets to rotate at different speeds depending on how far away they were from the sun. And in fact, there's a relationship that Newton worked out between the distance of a planet from the sun and its speed and the mass of the sun. So by looking at the motions of the planets, you can work out how much the sun weighs. So this was really important. So studying the orbits of planets basically enabled Newton to come up with the theory of gravity. So you could think about doing the same thing in a galaxy. And this is what Vera Rubin tried to do. She was just interested in the ways that galaxies were shaped more than anything. So there'd been some sort of inklings that dark matter might be a thing from as early as the 1930s. But a lot of the measurements were not done particularly well, and nobody really believed them. So she just set out to look for the motion. She just wanted to know, what do stars and gas do when they move around the outsides of galaxies? And she had access to an amazing new piece of equipment that was developed. This was in the 1970s, that was about 20 times better at collecting light than the cameras that they had during that time. So that enabled her to look for very, very faint light on the outskirts of galaxies. And she expected, as everybody else did, that the further out you are from a galaxy, the slower the gas and the stars should rotate. So gas in the middle will be moving fast, gas on the outside will be moving more slowly. But what she actually measured, hopefully this will come up in a minute. Okay, so what she actually measured was that even on the very outskirts of the galaxies, where there are very few stars, these stars and gas are still rotating really fast, basically as fast, or sometimes even faster, than the gas and stars in the center of the galaxies. And this, was pretty weird. This didn't seem to make much sense. So if we look at this graph again, so what was expected was that the speed of rotation should drop off as you go far away from the center of the galaxy, because the center of the galaxy that's like the sun in the solar system. That's where most of the stars are. That's with a really strong source of gravity. So that should be where everything is orbiting around. So you'd expect the rotation speeds to drop off. But what she actually found was that they just kept going. They were still as fast as they were in the center as they were right to the edge of the galaxy. And what did this mean? So I think she said for the first one she found, she almost didn't believe it. Like, she didn't know. She was trying to think of what possible causes could this be. But she did this for hundreds of galaxies and found exactly the same thing. And this really led to, this is the strongest evidence for there being something else, some other mass inside the galaxy that stopped these galaxies from just blowing apart. If there was no other mass in these galaxies would just blow themselves away. But there has to be extra mass inside these galaxies that's keeping them moving around. And she worked out that there has to be at least 6 times as much of this invisible mass as there is of all of the stars and gas in these galaxies combined. And this is what we now call dark matter. Okay. Okay, you can't really see this. But I just wanted to remind you that she was doing this at a time when being a woman in astronomy was kind of a rare thing. So if you can see it on the other screens, I think it comes up better. But this was this incredible headline in the Washington Post in 1950, which was when she presented her master's thesis at the American Astronomical Society, which is an annual meeting. And the headline is, "Young Mother Figures Center of Creation by Star Motions." So I think she obviously caused a stir at this meeting by being a young mother who did some physics. In fact, the last paragraph also reads, I don't know if I can read it from here, but it reads that the astronomers were not complimentary. So it took her a while to be accepted by the community. But today, I'm sure everyone in this room has heard of dark matter. And if it wasn't for Vera Rubin, we probably wouldn't have known about dark matter, that it really is a thing for a long, long time. She showed without a doubt that these galaxies had to have all of this extra mass in. This is the halo that Mike was talking about. If you go to the next slide, actually. Yeah, so this is hundreds of these galaxies that she looked at. These are from her actual measurements, and you can just see they're just flat all the way, for tens of thousands of light years outside of the galaxies where the light of the galaxies is. So this is the dark matter halo. And this is, a huge development in modern physics. She, really revolutionized the way that we view the universe. And she spawned entire new fields of physics. Like, we wouldn't have several fields of physics if it was not for this measurement. And also spawned varieties of protein powder. So it's kind of strange. But yeah, so this was really a huge measurement, and during her career, she was awarded many of the highest accolades you can get in science. So she was awarded the Gold Medal of the Royal Astronomical Society in the UK and the National Medal of Science here in the US. Though notably, she didn't get a Nobel Prize, which I think many people believe that she should have done. So it's a sort of sad part of the story.
Yeah, so this is just a picture I like. This is showing Vera Rubin doing these measurements with this new instrument that she had access to and was the first person to think about doing these measurements that then led to this incredible discovery of dark matter, or the confirmation of dark matter. And yeah, I think a lot of astronomers agree that is totally Nobel Prize winning discovery. And yet, she didn't get it, and it's very sad. And the sadder thing is, in the whole history of the Nobel Prize, only 3 women ever got it in physics. And so there's clearly,
2 women.
2?
Yeah, Marie Curie got it twice.
Oh, okay. So, right. Well, she got 1 in chemistry and 1 in physics.
Oh, maybe
But so there's definitely some bias going on here with the Nobel Prize committee, and I think Vera Rubin is really a big example of if someone deserved a Nobel Prize and didn't get it, it was her, and it's a shame that she now won't be able to get it. But yeah, Marie Curie was the first one in physics, and at least according to the story, it's like they wanted to give it to her husband. And he said, because they worked together, and he said, no, she did all the work, you need to give it to her. And that's half of the women in astronomy that got a Nobel Prize because of that. So yeah, so you should write the Nobel Committee that you're really not happy with that. Okay. Another little interesting news article that came out a couple of weeks ago at the American Astronomical Society annual meeting, which is like the big astronomy meeting that happens every year. Someone is predicting that we're going to see a new red star in constellation Cygnus in the year 2022, plus minus half a year. At this position in the sky is going to appear a new red object in the sky. So this thing is called a red nova. It's going to appear for a few months and then disappear. And so this is a prediction. This is an amazing prediction. This is one of the reasons I like astronomy better than astrology, other than, astronomy being correct, is that we get to tell the stars their future, which I think is much cooler than thinking they can tell us ours. And so what is happening here is there are actually 2 stars at that position that are now too faint. We can't see them with the naked eye, but we can see them in telescopes. And they're orbiting each other. It's a binary star system, and they're in a very tight orbit. In fact, they're so close to each other that their outer parts have merged, and they look like this kind of bowling pin-shaped thing. But it's actually 2 separate stars that are very close to each other, and so they kind of get into contact like this. And they're spinning around about every 11 hours. And so these people measured these orbits and noticed that in the last few years, the orbit is getting shorter, which means the stars are getting closer together and orbiting faster and faster. And if you extrapolate that trend, you get to the conclusion that in around 2022, they're going to merge. And when they merge, we get this bright flare called a red nova. We've seen other stars do it, but we've only seen it, once it happened. This is the first time ever someone has seen a system that might turn into this and predicts that it's going to happen. And unlike everything else in astronomy, where it's like, yeah, astronomical terms, this is going to happen really soon, like in 1 million years. This is going to happen now in 2022, which is really an amazing prediction. And also, these mergers are supposed to be super rare. And this one's going to be close enough that when it merges, the prediction is we're going to be able to see that with the naked eye as this new red flare in the sky, and then disappearing after a few months. And so, it's like 2022.2. So that's like 2/10 of a year. It's like March 2022 plus minus 6 months is what they're saying now. As we keep monitoring this, I think that prediction is going to get better. And it'll be interesting to see. And it's great for us because this constellation Cygnus, the swan, is right overhead for us in the summer. So it'll be very easy to see. Hopefully it happens around the summer and we'll be able to see it. So we'll see if this happens or not. It's a really risky thing for these astronomers to make this bold prediction, but that's what science is about. So we'll be able to see if it's correct or not.
Okay, so talking of other bold things you can do in the universe. So NASA have announced 2 new missions that they're launching in the early 2020s to explore the solar system. So this is specifically to explore the young solar system, so bits of the solar system that formed at the same time as the entire solar system formed. So the first thing they're going to do is, with a probe that's called Lucy, they want to go to something called the Trojans. And the Trojans are 2 groups of rocks which are in orbit with Jupiter. So Jupiter is going around the sun, and then there are these 2 groups of rocks that are following it. One's following it, and one's slightly ahead of it. So they're kind of like stalking Jupiter. So Jupiter's a really, really massive planet and actually has a huge gravitational effect on a lot of the other things in the solar system, including Earth. And it's probably basically captured these random rocks from space. We don't really know what they are. So they could be like comets or asteroids or even things from the Kuiper Belt, which is this huge cloud of other rocks further out from the solar system. So this probe Lucy is going to do a sort of crazy loop around the solar system to get to one side and then loop back round to get to the other side and really find out what these Trojans are. The other probe is a probe called Psyche, which is going to go to another rock, which is this rock here, which I think is I'm assuming is an artist's impression. You didn't label it, yeah. So this is a rock called 16 Psyche, which is an asteroid. It's one of the largest asteroids in the asteroid belt, which is between Mars and Jupiter. And this thing is really weird. So it seems to be entirely made of iron and nickel. And it's the only thing like this in the solar system. It's just iron and nickel. And that's actually very similar to the Earth's core. We think the Earth's core is pretty much just iron and nickel. So this thing is probably a core of a failed planet. So in the very early solar system, this thing could have been a planet that was about the size of Mars. And then lots of like violent collisions are happening in this early solar system when all of the planets are being built. And this thing basically got bumped around by lots of other things and lost its outer layers. So it's just the core that's left. So this probe, Psyche, is going to go visit this asteroid and really help us understand what the core of a planet is like, because we can't go to the core of our own planet. There's a lot of other stuff in the way. So this is our only opportunity to see what the core of a planet is like.
Yeah, and essentially this thing they're sending is a magnet. So, it's a metal thing. You send a magnet and see what happens. So that's going to be a pretty neat mission to see this stuff up close. Okay, last story, or a couple stories. SpaceX launched their rocket again last Saturday from Vandenberg Air Force Base, just around the corner here. And this is news because their previous one blew up 4 months ago on the launch pad. And so they had to stop. You'd be surprised how many things this affects, because they're supposed to launch some astronomy satellites as well, and the whole schedule got brought out. You can actually see, I think Santa Barbara is somewhere down there. This is from the rocket. So this, wanted to show you this video for a few reasons. So if you were watching last Saturday up in the sky, you could have actually seen this. It was a very clear day, as you can see. And then one of the things they did, so they sent this rocket out. It had 2 parts. the first part, or stage 1, goes back down, and stage 2 is sent to the higher orbit to do what it needs to do. And this stage 1, it comes back to Earth. So this is what SpaceX does in order to make space travel more affordable, and eventually something we can all maybe do, is you can't just throw away this half of your rocket. You want to bring it back and use it again. So this thing has to fly out into space and then make a U-turn, flip around, come back down, and then land on something. You notice it launches over the ocean, so it needs to land on something in the ocean. So this thing is fully robotic. No people are intervening in this. It's all automatic. And it lands in a barge, which is also totally automatic. It's a drone barge that goes out to the ocean to pick this thing up right where it's landing. So it has to be super precise. And so you're seeing this thing coming back down to Earth. This was broadcast live when it was happening. It was very exciting. You're seeing this thing come back down to Earth. You're going to see the barge show up in a second. And then it needs to nail this landing on a tiny little barge in the middle of the ocean. So it burns the engine there to slow down. And it's going to appear in a second. And hopefully you're going to be able to hear what the control room at SpaceX sounded like when this was happening. There it is. Yeah, that is pretty impressive. So yeah, a robot rocket ship landing on a robot drone in the middle of the ocean. After having deployed this was just a secondary goal of the mission. The main goal was the second stage that kept going and deployed 10 communication satellites into orbit. 10 Iridium satellites. I don't know if you've heard of the Iridium system. These are phones that you can supposedly just have reception everywhere on Earth, because they go directly to a satellite. So they deployed 10 of these. It's the first 10 out of 77 that they're going to deploy for this satellite network. So that's a lot of satellites. And in fact, there are already a lot of satellites orbiting the Earth. This is an actual depiction of how much stuff we have orbiting the Earth. And even just at what we call low Earth orbit, the nearby stuff, there's a ton of them. So there's like 40,000 pieces of stuff we send into space. That's the number of pieces we're able to track, or that's the number of pieces that are tracked publicly. So other than that, there's a bunch of classified stuff. And other than that, there's like millions of tinier pieces of things that are just floating around. So this is becoming an issue because it's getting pretty crowded up there. And if these things collide, it's a problem because it gets even more crowded, because all of the debris from a collision makes even more pieces. Okay, remember the opening scene in Gravity. If you've seen that, it's not good. Okay, so there was actually a couple of weeks ago, January 7th, was an alert. So there's a Joint Space Operations Center tracks these things and sent out an alert that looks like there are 2 satellites that have a 40% chance of colliding in a few days. And these are very big weather satellites, and they're not controllable. You can't move them. So basically, if they're about to collide, there's nothing we can do about it but watch. And so this was a prediction, and these are in an orbit where there are lots of these unmaneuverable satellites, and so it was a big fear that if they do collide, send out a bunch of debris, and that might cause other satellites to collide, and then you get this cascading effect. And eventually, it seems like it turns out we're really close to the point where if 2 satellites collide, this cascading effect will just go on until we're just full of debris around the Earth and can't launch anything for like 100 years until this clears. Okay, so this is an issue. Luckily, those 2 satellites did not collide. So that went by safely. But in 2009, the last big collision was in 2009. We had 1 Iridium satellite and a Russian weather satellite, I think, that hit each other. That's the orbits. They hit each other. This like one just T-boned the other at 26,000 miles per hour, and caused debris to fly everywhere. And there's like 2,000 pieces of debris. That's at least what we can track. came out of this collision. And it was so much that a few years later, the International Space Station had to maneuver away from a piece that was coming towards it. These things, even if they're small, they're moving so fast, they could just destroy the space station or any other satellite. So in 2000 and, when was this? A few years, 2011, they had to make a maneuver in the space station to move out of the way. And another piece came very close a few years later, and they just sent the astronauts to their Soyuz capsules in case something would happen and they would have to escape. And so luckily they were able to avoid that, but this is a serious problem. Also, a few years ago, China demonstrated they can destroy satellites from Earth. They fired a laser at a satellite and blew it up. One of their own, just for a demonstration, but the debris is still hanging around. This image here on the right shows you where there are pieces of debris from this satellite they blew up. And this thing just stays in orbit. It takes a really long time to fall back to Earth. So another piece of news that came out this week was that the Japanese are here to save the day. And they've invented this thing that they're going to try out. So it's a little satellite that sends out a smaller little thing, like a tug, and that can attach to a piece of space debris you want to get out of the way and just throw it in some direction where it doesn't pose a problem anymore. So this is an experiment. No one's ever done this before. So they've actually already sent this thing to the International Space Station, and when it undocks, they're going to try this out and see if it works. Just see if they can, stretch out this thing. It's like 2,000 feet long, and then see if that, if they can maneuver it around and maybe in the future try and grab satellites and start cleaning up all of this debris we've made in Earth orbit. Now, this news story, as you know, news outlets tend to find these stories and think of very creative titles for them. I was really disappointed by NPR came up with this. Come on. A little bit more class I would have expected from NPR. Okay, that's our news for today. We're going to take another short 5-minute break, and we're going to be back with Greg to talk about black holes. Okay. We are going to get to our second presentation today. We actually already got a good question about this presentation. I don't know how. Speaking of the questions, I heard there are plenty of postcards and posters in the back. So if we chose your question, please go claim your postcard or poster. And if not, there's a good chance we'll have some left at the end for you. Okay, so Greg is a postdoc at UCSB. So he got his PhD and is now doing research as a postdoc here. But we want to tell you a little bit, as usual, about Greg not as an astronomer. So Greg likes to run. Like a lot, like really a lot. This guy runs, I think like 90 races, of which he failed to finish only one, and that was because he ran into a pole twice. So he didn't finish that one, but he did finish all the other races. And these are not just normal races. I think like half of these are like these super marathons. There's like a few of these that are 100-mile races. And yeah, I don't even know how, I can't even conceive of that. But one of them that he ran was even longer than that. There's one that was over 500 miles. So this takes like a week, right, or more. You have, part of the race is you have to go to sleep and eat and, do other things that you do during the week while you're doing this race. So this was a race that's 888 kilometers or 555 miles. And so if you go to the website of this race, you can actually register for it. There's a bunch of different races you can register for it. Like, yeah, I'm dead at the 8-kilometer one already. But, so it's hard to see, but all these buttons says like register here, register here, register here. But then the 888 kilometers button says, you will regret this. Okay, so, but not only did he run that race, he finished it in under 8.88 days, which is apparently the time you want to beat here. And not only did he finish it, I found this poster. This is like him finishing it at like 2 a.m. someday. And got yeah. And so he's holding, I think it's maple syrup, is that correct? Is that what you get when you finish? Okay. And a certificate that if you look at it closely actually says first place. So, yeah, very impressive. So let's welcome Greg to tell us about black holes.
Thank you. Great, thanks, Yer. All right, so I want to just clarify up front that I'm not a real doctor. I don't have the stomach for it. I get sick on a swing. Instead, I'm what's called a postdoc here at UC Santa Barbara, which is just a glorified way of telling you that I'm in the 24th grade. And so the title of my talk is Black Holes, Nature's Beer Goggles. So let's just get the jargon out of the way up front. Beer goggles are used to refer to the supposed influence of alcohol on one's visual perception, whereby one is sexually attracted to people who would not otherwise be appealing. So let's start with a thought experiment. Here I am, standing before you, before your sober, thirsty eyes. What would I look like if you knocked back a few? Suddenly, I have a stunning resemblance to Ryan Gosling. Now, this is a very weak beer goggles effect, but trust me, too much alcohol consumption does wonders on your visual perception of things. So by the end of my drunken rant or educational public outreach talk, I hope to impress upon you that black holes act like nature's beer goggles. But before we can talk about black holes, we need to understand gravity a little bit. All right, so gravity is the reason we wear belts around our pants, and it's what imprisons us to the surface of the Earth. But I've got an escape plan. All you have to do is launch yourself off the surface of the Earth fast enough so that gravity can never bring you back down. So you might first try jumping. And if you're a good jumper, maybe you jump at like 7 miles per hour vertically up. You get like 18 inches high, but then gravity brings you right back down. All right, so that doesn't work. Maybe you borrow a rocket ship. Now, if you launch this rocket ship off the surface of the Earth at 7 miles per second, then you escape Earth forever. Now, this is not so fast in the grand scheme of things. It's only something like 0.004% the speed of light. Okay? So that's not so fast from the perspective of light. Yet it's difficult to do for us, right? Now here is the sun. Suppose you wanted to launch yourself off of the sun. The sun has 28 times more gravity on its surface than Earth does. So you'd have to go 28 times faster, or 0.1% the speed of light, in order to escape from the sun. Now, we've never sent anything going that fast through space, but it's still pretty wimpy relative to the speed of light. And so this is like a very minimal security prison. So suppose you've got the warden from the Green Mile, and he's kind of miffed because all the prisoners that he's put on the sun are flying spaceships into his head. All right? And so what he wants to do is build at least a medium security prison so that the prisoners can't escape. So he consults with an astronomer in the 24th grade to give him a tour of our galaxy. And the question he's after is, how can I make it harder for these prisoners to escape? So I'm going to try to find, a nice site for his medium security prison. Our galaxy itself contains 100 billion stars. It's 100,000 light years side to side. It bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide. We're 30,000 light years from galactic central point. We go round every 200 million years. And our galaxy is only one of millions of billions in our amazing and expanding universe. All right. Now, I found a great site to put this medium security prison. It's right here. And 1,000 years ago, in the year 1054 AD, a massive star exploded. And it left behind what we see today as the Crab Nebula, a blast wave going through space. And if we look toward the center of the Crab Nebula, we see a pulsar, which is a rotating neutron star. And so here we've got, really it's going around 30 times a second. It's going much faster than that. But a neutron star is 2 suns crammed down into the size of Santa Barbara, all right? Atomic nuclei are like literally touching each other. You guys are a hard crowd to impress. That is crazy. And so that's where we want to put our medium security prison, on this neutron star, all right? So we do that, but we can still escape if we go 33% the speed of light. So we do that. But here's Percy. Percy is the prick warden from the Green Mile, right? And he insists on a maximum security prison. A medium security prison will not do. And in conceiving of this maximum security prison, he gets to thinking, with his beer goggles off, what is gravity? So if you've been to a previous Astronomy Untapped, there's a demonstration here to answer, what is gravity?
It's the curvature of space-time. Like this bocce ball curves that space-time. And then, say, take a marble, that mass has to follow that curvature. And so it has to fall in. This is the same reason why if you jump up, you fall back down to Earth. Now, that's not the only thing you can do. So, I mean, the Earth doesn't fall into the sun, right? Because it's in an orbit. Let's see if I can do that.
Okay, so we sort of understand gravity now, the wimpy kind of gravity. But Percy wants a maximum security prison. So we need more gravity. Put on your beer goggles.
But what happens if an object is much, much more massive than the Earth or the Sun? In theory, it could warp the fabric so much it would create an actual hole in space-time. Once something fell in, it couldn't escape, not even light itself.
Okay, we have a black hole. You literally cannot escape from a black hole, even if you go at the speed of light. Which means that black holes are fundamentally invisible. And just as a fun fact, the first person to realize this, or to conceive of what a black hole is a guy named John Mitchell in 1784, which is 150 years before toilet paper was advertised as being splinter-free. This guy was way ahead of his time. All right? So black holes are fundamentally invisible. Okay, but we know they exist and we can see them. How do we do that? All right, so beer goggles off, okay? Be serious. This is a picture of our galaxy, okay? Now, if we point telescopes toward the center of the galaxy here, and we just track the orbits of stars for a couple of decades, we can see how they move. And the trajectories of those stars tell us that there's something they're orbiting that's something like 4 million times the mass of the sun, and it's in a very, very tiny space. So the only thing it could be is a black hole with 4 million times the mass of the sun. So Just for shits? Let's fly into it. All right, so we're going to fly into the supermassive black hole at the center of our galaxy. Here we go. So in the foreground, you have the black hole, and in the background is the galaxy. And so when you have an alignment between us on the Earth and then the black hole and a star right behind it, you get this ring of gas around the black hole that we call an Einstein ring. Now, another fun fact, the alignment of three things like this in astronomy is my second favorite word. It's called a syzygy. My first favorite word being defenestration. Okay, so this is the Einstein ring, and we continue to fall into the black hole. We're going toward the black hole. We're going to fall inside of it eventually. Things are all crazy. We're getting closer and closer. All right, this is a point interior to which it's impossible to maintain a circular orbit around the black hole. So you have to be really smart about how you fire your thrusters at this point if you want to escape, because we're getting close. Let's go closer. So we're going closer and closer into the black hole. When will we get there? All right. We're inside the black hole, which you may be confused about, right? Nothing crazy happened. Space didn't explode. You didn't even really notice anything change. Well, it turns out light cannot escape from a black hole, but it can go into it just fine. So if we're inside of a black hole, light can still get in, and we can still see light from outside. So you can fall into a black hole and not even notice that you've fallen into the black hole. But now we're in it, and we continue to go all the way down to the singularity, and right before our awesome death, this is what we see. Okay, so we just fell into the supermassive black hole at the center of our galaxy. But most black holes in our galaxy are not supermassive black holes. They're much smaller black holes, something like 10 times the mass of the sun, and they're just littered throughout the galaxy. We think there are maybe something like 10 million of these distributed throughout our galaxy. But we only know of about 24 of them because they're hard to find. Black holes are fundamentally invisible, remember? All right. So you might have heard recently about two black holes merging together. These are relatively small black holes, each about 30 times the mass of the sun, and they're merging together here, and time is slowed down in this simulation by about a factor of 100, just so you can see them merge together and to ultimately create a single black hole. And this is super new science, and I'm sure it's been talked about here at Astronomy on Tap before. And now they're one. Okay. So those are all fancy computer simulations. It's not what we actually see with our telescopes. So what do we actually see with our telescopes when we point them at one of these smaller black holes in our galaxy? A black hole with, say, about 10 times the mass of the sun. This is what we see. And so this is X-ray light from a telescope, observed from a telescope in space of a black hole in our galaxy. Now, by very carefully studying this X-ray light, astronomers think that if we could spatially resolve everything, what we would really see is something like this. All right, let me explain this a little bit. I know it's a hard sell. But what we have here is a black hole in an orbit with a star. Now, they're very close together. You know, the Earth goes around the sun in a year, right? These things orbit each other in a matter of hours. So they're very, very, very close. And the black hole is much more massive than Earth, like 10 times the mass of the sun or so. So it can actually rip the gas off of the star toward itself, okay? But because this whole thing is rotating, that gas winds up forming a disk around the black hole, and that gas is very, very hot, like 10 million degrees hot. You know, your body is something like 100 degrees Fahrenheit, and you emit infrared light, okay? You know, you put on those infrared goggles, you can see people's body heat. If your body was 10 million degrees, it would emit X-ray light. Well, as Mike told you, actually, there'd be issues. Atoms cannot exist, et cetera, et cetera. But it's the same sort of idea. And so what we observe is the X-ray light from this disk of gas, okay? And we use that to infer things about the black hole. Now, this is with your beer goggles off, what we think you would see. What if you put the beer goggles on? Suddenly, the disk might look something like this. A little bit weird. And you might kind of recognize it from the movie Interstellar, right? And so what's happening here, on your left side, gas is going toward you, all right? And that gas emits light, and because it's going toward you, it gets boosted toward you and is much brighter. But gas on the right side is going away from you, and so it gets boosted in the other direction and is dimmer. Now, what about this weird kind of lump on the top here, all right? This is because the gas in the disk behind the black hole will emit light, and that light has to go by the black hole to your eyeball, and as it's coming by the black hole, it gets bent like this. So that's sort of why the disk looks all funky like this, all right? And so this hump is an inclination effect, which is what I'm going to show you with a Frisbee. Psst, Cassie. Whew. That's what I was most nervous about tonight. And, okay, so here I'm going to show you a movie of one of these disks of gas, and it starts off face on. And then I'm going to start tilting it. Why don't I just do it, because it's kind of a long movie. All right, here we go. And as I tilt it more and more and more, the gas from back here is going to have to pass over the black hole in order to get to your eyes. And as it does that, it gets all bent. And that's why you see this kind of hump at the top here, okay? And so now the disk is pretty much edge on. Okay. But you can also, believe it or not, see the underside of the disk for the same kind of reason, because light that's emitted on the backside of the disk can get bent around to your eyeballs, and you see this underbelly of the disk. Okay. Now, I want to stress that this is all an illusion, you know, because it's the gas that's emitting the light. Now, the gas is just in a plain disk like this, and the light looks all wonky, okay? So if you were to go reach out and touch that spot, there'd be nothing there, because the gas isn't there. It's just an illusion, because the black hole works like beer goggles and bends the light all crazy like. Okay. So here's a cool movie.
That looks like an eye in the sky.
That's a black hole, a totally invisible region of space-time.
Invisible? But it's all red.
That's the incandescent gas which it swallows up, which glows before disappearing. See, the black hole distorts space around it so much that the images are totally warped. It's as if space-time was soft.
That's amazing.
I know. Okay. So now, I get to tell you about my research. So these disks around these black holes, where you have a star orbiting the black hole, right? Suddenly, they can get 100 times brighter than they were just a day before. And they can also eject this gas into space along with these sort of jets that are just driven out into space as well. Now, why is that? Well, we don't know. This is an active area of research. So what I've been working on recently is to consider the effects of magnetic fields in these disks, okay? And that's what these kind of blue lines are trying to show you. That's like a magnetic field in the disk, okay? So it's very difficult to simulate in high resolution, like on a supercomputer, the sort of stuff that Mike was showing you. It's hard to simulate the entire disk. So what we do instead, we just pick a patch of it. And we let all the gas kind of flow through this patch of the disk, and we only simulate this little patch. And that's what I'm showing you here, little patches of the disk, okay? And the one on the left has weak magnetic fields, and the one on the right has strong magnetic fields. And the color, red or blue, is showing you if the magnetic field is pointed, like this donut of magnetic field in the upper picture, the color is showing you if it's pointed in a clockwise direction or a counterclockwise direction. So all I want to impress upon you here really is that weak magnetic fields behave differently from strong magnetic fields. And what we're working on now is trying to determine some observational consequences of that. But it's a work in progress. So that's what I wanted to share with you. And all I really want you to take away from my long drunken rant is that black holes are real. And as you stumble home tonight, just remember that they act like nature's beer goggles. Great, thank you.
Okay, thank you, Greg. That was awesome. Don't go too far away. So we'll do questions for Greg in a couple minutes, so keep texting them in. We're not going to have a break. We're just going to go straight to the end. So keep texting questions, and then we're just going to go over some upcoming events and the next Astronomy on Tap, I think. So, yeah, stay there. Okay.
Yeah, you're going to have to use this because it doesn't. Okay, where did our remote slide thing go? Oh. Okay, so while you're texting in your questions for Greg, we've got already a few good ones, so keep them coming. I'm going to tell you a little bit about some future events we're organizing. And these are all organized by a place called Las Cumbres Observatory, which is hosting this event, and these other events I'm going to tell you about. It's an observatory right here in Goleta. So our next event is February 22nd. This is going to be a talk by Professor Lars Bilsten. So depending on whether you're following our observatory page on Facebook or not, you know that Lars recently won the Danny Henneman Prize for Astrophysics for the year 2017, which is a very, very prestigious prize. Lars studies stars, as his name would suggest. In fact, his class at UCSB is called Stars with Lars. And he's going to be giving a public talk. It's not going to be here. The location is yet to be defined, but we will let you know on Wednesday, February 22nd. So if you want to go to that, log into our website, and we'll have the information there for you. We also want to tell you about a very, very special event. Our next Astronomy on Tap is going to be on March 1st. So we're taking a little bit of a break in February, but it's going to be worth it because March 1st is our first year anniversary of Astronomy on Tap. Yep. Believe it or not, we've been doing this for a year now. It's also our 10th event. And so it's going to be a very special Astronomy on Tap. The format is going to be very different. And we are going to have some very, very special prizes for that event. We're going to be giving out a telescope, for example. Yep. This is a 5-inch telescope, refracting telescope we're going to give out. And that's the second prize. The first prize is going to be a visit to our telescope up in Santa Ynez Valley. A private star party for you and a small group of friends. A private tour of the night sky with a professional astronomer up here in Santa Ynez. So that's going to be given away in our next event as well. So make sure not to miss that if you're here on March 1st. Okay. I think it's time for questions for Greg. You good?
Okay, thank you. Lots and lots of questions for Greg, so we'll get through a couple. So this question I thought was quite interesting. So if a black hole is, so you're telling us that there are black holes that are 10 times the mass of the sun, but we know there are stars that are more than 10 times the mass of the sun. So why are they not black holes?
Is this on? Yeah, okay. So stars are able to resist gravity. They have ways of doing this because they're composed of gas. So things like gas pressure and radiation pressure can fight off gravity. But when you run out of a way to resist gravity, gravity will just crush you down to a point, and if you have a massive enough star, you will form a black hole.
So a couple of people ask questions about why do these black holes develop these disks in the first place? So what are they made of?
What are they made of?
But, well, yeah.
Okay, so the reason the black holes develop these disks is because they're able to rip off material from this star that's very, very close to them. And it's so imagine that the Earth had puffed up enough that the moon could just easily rip off material from the surface of the Earth, right? The moon causes tides, it tugs on the Earth and on water. But if the Earth was loosely distributed, the moon could rip off material from the Earth. Here we've got a black hole that's much, much, much more massive, and the star is very puffy and distributed, and it's easy for the black hole to just rip material right off of that star toward itself, but it doesn't come straight onto the black hole. It forms a disk because the whole thing is rotating, and there's angular momentum in this system that will form a disk. Just like if you spin a ball of pizza dough, it will form a disk.
Okay, this one's a sort of esoteric question. So if black holes are infinitely small, how can two black holes merge? How do they even touch?
Yeah, actually, so we don't really know. That's a really hard question.
I don't know if you can answer that.
We don't really know.
Okay. Yeah. Okay, maybe this one we can answer. So a couple of people also asked, I think you didn't really talk about this, but you see these jets coming out of black holes too. What are they and what are they made of? What causes those?
So, again, we don't know for sure. That's sort of the answer always, right? And the other answer is it's magnetic fields. So we think that magnetic fields are responsible for launching these jets away from black holes. But that we don't know that definitively. But the leading models for these jets appeal to magnetic fields.
Okay. If black holes suck everything in, do they...
No, black holes don't suck.
Oh, okay.
Black holes don't suck. If the sun all of a sudden became a black hole, but it kept its same mass, nothing would happen to the Earth. It would continue to orbit around the sun. Granted, it would be very, very cold, and there would be no more sunlight, but computer science majors wouldn't even notice. But yeah, black holes don't suck things in.
Okay, well, the end of that question was do they conserve information? Do you want to talk about black holes have no hair?
Do they conserve information? So the way I'm going to interpret this question is that I can make a black hole out of anything if I squish it down enough. If I take the Earth and I squish it down somehow to the size of a marble, it will become a black hole. If I took your mother-in-law, who happens to weigh as much as the Earth, I know, low. And if I squished her down to the size of a marble, she'd also become a black hole. And these two black holes are indistinguishable from each other, okay? If you showed me both of them, I couldn't say which one you formed from the Earth and which one you formed from your mother-in-law who weighs as much as the Earth.
Okay, yeah, this sounds good. Do you want to end on a strange one?
Let's do it.
Okay, I like this. What are the odds that Earth could fall into a black hole? Except black holes don't suck, so that might not happen. That we haven't seen yet. Quick.
Small.
All right, thank you very much, Greg.
Okay, yes, it is time for our raffle. Let's show you what you're playing for here. These are beer glasses that say Astronomy on Tap on them and Las Cumbres Observatory on the other side. Collector's item. We'll be giving out 4 of these. Just right before we do this, I want to ask a favor of everyone here. So we've been doing Astronomy on Tap for over a year, and we actually have a question for you. A very simple question. Who are you, people who come to Astronomy on Tap? We would really like to know. Not, it's great that you're coming here, and we're curious as to who you are and what we can do better. So if you have a phone that can scan a barcode, please scan the one right here on the screen, and on your way home, answer a very short questionnaire that we have prepared just to see who, we want to understand who you are and how we can maybe improve these events and make them better and make them more interesting and more engaging for you. So you can either type that code or go to that very confusing URL. And we're going to leave this up while we do the raffle so that you can help us out with this questionnaire here. And it's completely anonymous, and you can answer any of the questions there that you want. You don't have to answer all of them. So whatever you feel like, and it's totally anonymous. Okay, we are now, I'm going to have to take this off for a second, but we'll bring it back on later. Going to raffle these beer glasses. So you should all get out your raffle tickets. There should be a number on it. We're going to do this the easy way here. So you should have a number between 1046 and 1305 on your raffle ticket. Yes, we are using Wolfram Alpha for this. It's much better than, reaching into a bowl of things. Okay, so we're going to do the first one. Where is it? There it is, 1096. 1096, if you're here, come on up and we'll give you your beer glass. If we call your number, come on up and we'll give you your glass. If you don't, we'll give it to someone else. 1096. Okay, excellent. Next one. 1213. Is 1213 here? Okay, we'll give you a second to come on to the front and get your beer glass if you're here. 1213. Is there a 1213? Yes. Okay, making their way. Good. Okay, next one. 1189. Is 1189 here? 1189. Okay, if you're here, you have until the next number to come up. 1189, perhaps. Okay, we're going to give you one more, and then if 1189 doesn't show up, we'll do another one. 1118. Is 1118 here? Yes? Is it? Yes. Okay, 1118 and 1189. Are you here, or are we giving your glass to someone else? 1118 is here. Okay, great. I think 1189 is not. Okay, that silence confirms that. So we're going to do another one instead of 1189. Last one. Everyone ready? 1220. sounds like there's a 1220 or something close to it. Is there 1220? Yeah? Okay. Sounds like there's a 1220. Okay, so don't forget next Astronomy on Tap, March 1st, our first year anniversary, very special event. Please stay in touch. Please answer our questionnaire. Let's give another round of applause for our two great speakers today. And we want to thank the Matrix for hosting us here every single time. And thank you for coming. And thank you, Charlotte.
Thank you, Yair, for
And we'll
organizing
see you-
everything.
We'll see you next time.
Okay, and don't forget, talk to people with stars about astronomy.